Welcome back. I'm here on behalf of Forge College, and today we're tackling our next major step, compiling contracts and inspecting build artifacts with Hardhat. In our previous lesson, Runtime Conflict Detection and Resolution, we learned how to untangle errors so our initial designs are rock solid. Thanks to that work, our proverbial factory won't catch fire the moment we turn the machines on. But here is the catch. A perfectly written Solidity smart contract is actually completely useless to the Ethereum blockchain on its own. That code is formatted so that we can read it. The blockchain's machines cannot. This diagram shows exactly how to bridge that gap. Think of your Solidity code as a flat paper blueprint. It tells you what to build, but it isn't the building itself. The Hardhat framework is the automated factory required to actually manufacture the product. The act of compiling is simply pressing the start button on that factory. It takes your human ideas and translates them into machine reality. You cannot skip this step. Compiling is the mandatory, highly reliable bridge that converts your easily readable blueprints into the strict, actionable instructions that the Ethereum network requires to run. To start the machines, you open your terminal and run a single command, npx hardhat compile. When that finishes successfully, you will see a brand new folder pop up in your project directory called Artifacts. Looking at this diagram, you see how each source code file results in a newly created JSON file nestled inside that Artifacts folder. We call this the artifact. Think of it as a heavy, dense shipping container packed with data. This single JSON artifact is the ultimate standardized box. It holds absolutely everything your testing environments and deployment scripts will ever need to interact with the contract. Now, this diagram shows what happens when we crack open that JSON shipping box. We're hunting for two critical items. First is the bytecode. If the contract is a robot, the bytecode is its brain, a massive string of machine instructions, always starting with 0x. There is a slight nuance here. The main bytecode field is used to initialize and deploy the contract, but there is also a field called deployed bytecode. That is the permanent runtime code that actually ends up living on the blockchain after the startup sequence finishes. Once our robot brain is deployed onto the network, we run into our next problem. How do we talk to it? That brings us to our second crucial item, the Application Binary Interface, or ABI. Think of the ABI as a remote control. Without it, you have no idea what buttons to press. The ABI defines your functions and exactly how to interact with them. You absolutely need the bytecode to physically place your contract on the blockchain. But the ABI is completely non-negotiable for actually communicating with it later from your front-end apps or your test scripts. In practice, carrying around that massive JSON shipping container every time you just want to press a button on your ABI remote is incredibly inefficient. The solution is to write a lightweight, automated node script that targets that large artifact file and extracts only the pieces we actually need. As this flow diagram illustrates, our script parses the heavy JSON and filters it down, splitting it out into two perfectly isolated files, one dedicated to the ABI and one dedicated to the bytecode. Both are routed right into a clean new folder called Build Inspection. By separating them, your front-end web components and your deployment scripts can now grab exactly what they require without needing to parse heavy, complex data files every single time. By automating this extraction, you create a process where every version of your code is matched to a specific set of files. This makes your workflow easier to track, so you can always verify exactly which version of the code you are deploying. To review the full journey, you write your Solidity code, you run the Hardhat compiler, you inspect the JSON artifacts, and extract ABI and bytecode. Automating this extraction removes the risk of manual errors. It ensures your local tests and your deployed contracts stay perfectly synchronized, so you never have to worry about digging through giant files to find a mistake. Thanks for joining me today. This video was brought to you by Forge College. To learn more about Ethereum dev stacks and to explore other educational Web3 topics, head over to forge.college and keep building.